Airbags produce nitrogen gas from the reaction 2NaN3 solid breaks down into 2Na solid and 3N2 gas. So we have a solid that decomposes to form a gas. If 2.25 grams of NaN3 reacts to fill an airbag, how much pressure volume will the N2 gas do against an external pressure of 1 atm, given that the density of nitrogen is 1.165 grams per liter at 20 degrees Celsius? So we get to bring some stoichiometry into this particular topic. That's what this problem is. And this problem's a doozy. It's a big one. There's kind of a lot happening here. But at the same time, we are looking at pressure volume work, and the equation for pressure volume work is that it's equal to negative P delta V. So what we ultimately need to find is what the change in volume will be when we make the nitrogen produced by 2.25 grams of NaN3 breaking down. So we're going to start at stoichiometry, and there's a couple ways we can tackle it. All these ways start with the 2.25 grams of NaN3. And in stoichiometry, we're always trying to work our way to moles. So we're going to use the molar mass of this compound, which I know you know how to do from the periodic table. It's 65.01 grams. And once we've gotten to moles, we can then switch substances. So from the balanced chemical equation, we know there's 3N2 for 2NaN3. So we want the 2NaN3 on the bottom, because that's what we're trying to get rid of, and we want the 3N2 on the top. Oops, I forgot moles in here, so this should have been moles. Okay, so 3 moles of N2 over 2 moles of NaN3, that's going to cancel out. Now we're in moles of N2. At this point in the problem, we could stop and use the moles of N2 and the PV equals nRT equation with the 20 degrees Celsius and the 1 atm, the moles, and the ideal gas law to find the volume. That would certainly be one option. Another option we have, though, is to use the density that's provided. So that's what we're going to do. We're going to convert back to grams. So 1 mole of N2 is 28.02 grams of N2. And then we're going to use the density and say that in 1 liter of N2, there is 1.165 grams of N2. Grams of N2 cancels out, moles of N2 cancel out, and this is going to give us an answer in liters of nitrogen. So whether you did this part or you use this part, you should end up getting the same answer for the volume of N2, and that is 1.25 liters of N2. This is going to be equal to the change in volume of the airbag. This is how much N2 gas is produced. It really doesn't matter how big the airbag started out before or after. It only matters what the volume change was, because that's what's in our equation is delta V. So once we have found the volume of N2, we're just going to plug that right into our equation. Work is equal to negative pressure is 1.00 atm. That's from the problem, times the delta V, which it increases by 1.25 liters. This will give us 1.25 atm liters, which negative 1.25 atm liters, which we can convert into joules using the fact that there's 101.3 joules in an atm liter, and that's going to give us a final answer of negative 126 joules. So the work done by the nitrogen gas expanding and filling the airbag is negative 126 joules. In the second part of this problem, we're asked to find the energy of the system during this process. So energy is made up of work and heat. We already know that the work is negative 126 joules. And now we're given the heat. And we're telling, the problem tells us that the process released 2.34 kilojoules of heat. So Q is going to be negative 2.34 kilojoules. There are 1,000 joules in 1 kilojoule. So the total energy change will be negative 2,340 joules plus negative 126 joules. We only have 3 significant figures here. Our final answer is negative 2,470 joules. Again, like problem number 5, I believe it was 5, this isn't a particularly hard problem mathematically. Part B isn't. Part A was tricky. Anytime we bring that kind of different stoichiometry and that many different things into a problem, it gets tricky. But part B is relatively simple as long as we recognize that the releases part tells us there's a negative sign there, and we remember to convert kilojoules to joules so that we're combining the same unit.